A paper airplane glides because space chooses how directions add up. That choice sets what structures can form and which fail. Change a rule and flight, chemistry, or clocks stop behaving. This is geometry at work, not whimsy. We begin with the oddest ingredient, the number of directions. Stick with a simple image, it helps anchor what follows. Picture a universe where every turn feels subtly too roomy. Dimension is simply how many independent directions movement can take. That count sets force shapes, orbit stability, and atomic architecture. In 3 dimensions, fields spread over spheres that grow as area. So gravity and electricity fade with distance as inverse square. Change the dimension, and the spreading pattern changes immediately. In 4 dimensions, spheres balloon faster, so forces drop cubically. That one tweak wrecks closed orbits and tidy atomic shells. Mechanistically, Kepler harmony relies on a precise inverse square. Deviate slightly and orbits precess, leak energy, or fly apart. Quantum mechanics is just as picky about the potential's shape. Hydrogen's bound states depend on that exact radial dependence. Push to 4 dimensions and the ground state becomes precarious. Electrons either plunge or smear, denying chemistry its periodic rhythm. Rule of thumb, 3 dimensions make forces just strong yet gentle. Too few and knots cannot hold, too many, binding fails. Here is a concrete check you can remember. In 4 dimensions, gravity fades as 1 over r cubed. Double the distance and attraction drops by a factor of 8. Close and everything collapses. Far, nothing binds for long. Life needs reliable scaffolding, and 3 gives that sweet spot. So the picture is, dimensionality quietly selects which realities persist. You send a ping to Mars, then stare at the silence. The universe answers on a fixed schedule set by C. That constant is the maximum speed any influence can travel. It decides which events can talk and which stay strangers. Draw a light cone and you map a loud cause and effect. Inside the cone, signals can reach. Outside, they never will. Relativity adds a twist. There is no universal now to share. Different observers slice time differently, while cones keep causality intact. Mechanically, motion squeezes time and stretches space along travel directions. Clocks moving fast tick slow, and rulers contract compared with rest. Those distortions are not defects, they preserve the cosmic speed limit. Example you can feel, Earth to Mars takes between 3 and 22 minutes. A rover command rides photons and waits through that baked delay. Our GPS works only because satellites correct relativity by microseconds daily. Ignore that, and your phone's map drifts kilometers per day. Tiny test, cosmic rays make muons that should die before ground. Time dilation extends lifetimes, so many reach detectors anyway. Net result, finite C fences stories, synchrony, and possible strategies. It turns the universe into neighborhoods with honest traffic rules. Bottom line, causality survives because nothing jumps the light fence. Stand by an imaginary black sphere, the ultimate cosmic locker. There is a surprising cap on information any region can store. Call it the Bekenstein bound, an area law for reality. It matters because memory, computing, and even recording histories have ceilings. Mechanistically, pack matter tighter and gravity pushes toward a horizon. At the limit, entropy scales with the boundaries area, not volume. The bookkeeping lives on the surface, like pixels covering a sphere. That quirk hints at holography, bulk stuff encoded on boundaries. Numbers help anchor it, so let's size a 1-meter horizon. Its maximum information is about 10 to the power of 69 bits. That dwarfs any data center, yet it is less than volume scaling. A solar mass black hole holds about 10 to the 77 bits total. Erase 1 bit and physics demands heat by Landwehr's principle. At room temperature, erasing 1 bit costs about 3 zeptajoules, so information limits are thermodynamic and gravity enforces the receipt. Overlay that with quantum fields, and area keeps winning the argument. Holographic dualities make entire volumes behave like boundary codes. 1-sentence recap, the biggest library fits on the skin, not inside. Space tells you how many stories can be written before collapse. Skim the rim of a heavy star and watch starlight bend. Curvature is geometry itself changing shape under mass and energy. That change directs motion, sets tides, and focuses light into arcs. In general relativity, free fall is straightest travel in curved spacetime. Matter tells space how to curve, and space tells matter how to move. Geodesics replace forces, while gradients become felt as weight. Tidal differences stretch or squeeze as neighboring paths diverge. Numbers make it real. Mercury processes 43 arcseconds per century. That mismatch baffled Newton, and Einstein's curvature fixed the ledger. Light grazing the sun deflects by about 1.75 arcseconds. Telescopes see galaxy clusters warping backgrounds into luminous rings. Those are Einstein rings, clean signatures of space itself flexing. Around black holes, spacetime curls so tightly that paths loop. The Event Horizon Telescope resolved a 40 microarcsecond shadow outline. That patch is like a donut on the moon seen from Earth. Mechanically, curvature changes distances and times between events. It even slows clocks deeper in gravitational wells measurably. One sentence recap: gravity is shape, and curves choreograph all motion. Pull back to a deep field, galaxies salted across black velvet. Expansion is space itself stretching, not galaxies speeding through ether. That stretch sets a moving horizon, what can ever contact us. Hubble's law ties recession speed to distance with one constant. Numbers again, around 70 kilometers per second per megaparsec today. Every megaparsec adds that speed, so distant space recedes faster. Nothing breaks relativity because it is space growing, not motion through space. Locally, gravity binds. Globally, the metric swells between islands. Mechanically, light from far galaxies swims against an outgoing current. Enough stretch and the swimmer never reaches our shore. Our observable radius sits near 46 billion light-years. Beyond that, light starting now can never arrive here. There is also an event horizon, smaller than the visible edge. With dark energy, that boundary is roughly 16 billion light-years. Anything beyond that today drifts outside forever, however patient we are. Example in real terms, future astronomers might see only our local group. Distant galaxies will fade redder and then slip beyond detection. Net result, expansion edits the possible conversations of the cosmos. Thread your gaze along the cosmic web, filaments stitched by gravity. Topology is the global connectivity of space, the shape of holes. It decides whether straight paths eventually loop or wander forever. That choice changes what can repeat and how cosmic maps tile. Mechanically, a multiply connected universe wraps like a hall of mirrors. Light can circle, showing the same galaxy from different directions. Patterns then repeat with measurable separations on the sky. Cosmic microwave background maps let us search for those repetitions. Matched circles would reveal a finite, yet unbounded global shape. So far, surveys have not found convincing matched pairs. That pushes allowed fundamental domains to sizes comparable to our horizon. In plainer words, if space loops, it likely loops very wide. Example, a small dodecahedral wrap would imprint twins we could spot. Those are absent, so tight wraps are disfavored by data. One sentence recap: topology can constrain echoes, and echoes seem rare. Zoom down between two polished plates, a shimmer hangs in nothing. The vacuum is a restless field, even when average energy looks zero. Boundaries change which field wiggles can exist, and that matters. Those changes create a tiny push, called the Casimir effect. It matters because nanoscale machines and chemistry feel boundary physics. Mechanistically, only modes that fit between the plates can persist. Outside, more modes exist, so pressures differ ever so slightly. That pressure imbalance nudges the plates together, and it is measurable. For plates 100 nanometers apart, the push is about 1 Pascal. Rule of thumb, it scales roughly as 1 over separation to the 4th. Experiments confirm the trend using torsion balances and microcantilevers. Engineers must account for it when parts sit extremely close. Example in real terms, a square centimeter feels about a millinewton at 1 Pascal. That seems tiny, yet it can stick delicate devices shut. Bottom line, empty space sets forces by allowing or vetoing vibrations. Aim the sharpest probe you can build and space pushes back. Uncertainty links position to momentum, setting a floor on certainty. That floor limits microscopes, colliders, and even your camera sensors. Shorter wavelengths resolve smaller features, but they carry more energy. More energy means stronger disturbance, which changes what you measure. Mechanistically, lambda equals h over p, a tight bargaining rule. To see tinier things, you must pay with bigger momentum. Diffraction also blurs detail through any finite aperture or lens. To resolve 10 to the minus 19 meters, you need around 10 teraelectronvolts. The Large Hadron Collider reaches 13 teraelectronvolts on good days. That buys glimpses near 1 times 10 to the minus 19 meters. Electron microscopes push down to about 5 picometers in practice. Below that, atoms themselves refuse cleaner portraits without violence. One sentence recap: resolution is a negotiation between clarity and disturbance. These rules aren't quirks, they are the rails under possibility. Dimension, C, curvature, horizons, topology, vacuum, and resolution quietly govern outcomes. They explain why structures hold, why clocks tick reliably. If that clicked, you now see how space edits reality. I'd love to explore these rails with you next time. Tap follow and bring a friend who doubts empty space. Share this with someone who loves strange, satisfying physics facts.